This is pre-class video on module 4 unsymmetrical fault analysis in power system analysis course. Myself Dr. M.J. Chandrasekhar, Associate Professor, Department of EEE, SABIT. In this module, I will be explaining the unsymmetrical fault analysis like LG fault and LL fault with introduction to unsymmetrical fault analysis. This is the first session on this module. The syllabus here is introduction, symmetrical component analysis of unsymmetrical faults, single line to ground fault, line to line fault, double line to ground fault, and open conductor faults. This is the syllabus is there on the module 4 unsymmetrical fault analysis. So, let us see what is fault. Fault is any failure which interferes the normal flow of current. So, faults are due to different types, external and internal faults. Here unsymmetrical faults are the faults in which the fault current in the three phase are unequal. The different types of unsymmetrical faults are single line to ground fault, line to line fault, double line to ground fault, and fourth one is open conductor faults. Open conductor faults. Symmetrical fault in the module 2 is there. In that the fault current is same in all the three phases. In this chapter we will be understanding how to analyze the fault current and sequence network for line to ground fault, line to line fault, double line to ground fault, and open conductor faults. The overall the faults you can broadly classify into shunt fault and series faults. Series fault is nothing but the one open conductor or two open conductor faults, that comes under open conductor faults, and shunt faults are this single line to ground fault, double line to ground fault, and line to line fault. Here whenever there is an imbalance in the system, the voltage and current in each of the phases are different. We have to use the concept of symmetrical components to solve the problem. The concept of symmetrical components and sequence networks will be used for the analysis of unsymmetrical faults. So, in the series faults we have two types. One is one open conductor fault, two open conductor fault. And if you see the experience of different faults from the many years, it is found that more frequently occurring fault is single line to ground fault, that is 70% of the faults are single line to ground fault, and more rarely occurring fault is symmetrical fault, that is only 5%, and line to line fault it is found that 15%, and double line to ground fault is 10%. So, let us understand what is the analysis with respect to symmetrical components of unsymmetrical faults. Here in this it is considered a transmission part of the power system. In this we have three transmission lines, namely A, B, C, and if the fault occurs on the line A, then the voltage drops to 0 and suddenly inrush of current IA takes place. Similarly for B phase and C phase. So, next we will see how to write the sequence network. So, this is positive sequence network, negative sequence network, and zero sequence network for that. So, here positive sequence network means it consisting of the positive sequence voltage and currents VA1, IA1, VA2, IA2, VA0, IA0. Next we will analyze the review of sequence networks for the generator. generator positive sequence network will be, suppose if you consider a generator, its positive sequence network, as I explained in the previous videos, this is positive sequence reactance and the source voltage. This is the positive sequence, and positive sequence means it has IA1 and VA1. So, the drop here is here Z1, positive sequence. Negative sequence means it is having only the negative sequence impedance and negative sequence current and negative sequence voltage VA2. Similarly, zero sequence of generator, if it is neutral grounded through Zn, then 3 times of Zn we have to consider. This is Z0, so Zz0. So, the sum of these two will be your Z0 and the IA0 flows and here VA0. If you write the KVL equation for the positive sequence and negative sequence and zero sequence, so we will write the equation for the positive sequence. Here VA1 is EA minus IA1 into Z1. Similarly, VA0 minus Z0 into IA0, VA2 is minus Z2 into IA2. So, these three equations we can write in matrix form in the next slide. So, these equations are written in matrix form. Here VA1 is EA minus Z1 into IA1, VA2 is minus Z2 into IA2, VA0 is here VA1 is EA minus Z1 into IA1, this is the equation. VA2 is minus Z2 into IA2, VA0 is minus Z0 into IA0. So, this positive sequence network, negative sequence network and zero sequence network. This is positive sequence network, this is negative sequence network and this is zero sequence network. This is very important for understanding the different types of faults under unsymmetrical fault analysis. So, next we will be considering the next derivation, that is single end to ground fault analysis on an unloaded synchronous generator. In an unloaded synchronous generator, see here this is symmetrical, that means phase A, whatever the quantities we have EAZ and EBZ, ECZ, all the three phases are symmetrical and such a system we have considered and the terminal of generator, that is A terminal is grounded. That means fault happened on the phase A. If the fault happens, then the condition for the fault. So, suddenly if the phase A is grounded, then voltage VA drops to 0 and IA will be your fault current. And the generator is unloaded, therefore, there will be no current in the lines B and C phase. So, these are the terminal conditions for the fault. Next, let us consider these initial observations in the calculations. In the next slide, I will be showing how we have taken care the initial conditions in the symmetrical component of currents. This is the symmetrical component of currents. This is given by the IS is equal to tau PS inverse into IP, This tau PS IS tau PS inverse is nothing but it is a constant matrix 1 1 1 1 A square 1 A square A. So, this tau PS inverse is taken here and this IP is nothing but the phase currents. How many phase currents here we have? We have 3, that is IA, IB, IC. IA value is nothing but fault current and then IA value is taken. IB and IC values are 0. So, that is what So, if you simplify this equation 4.2, you will get IA0, IA1, IA2, all the sequence currents are equal, and it is equal to IA divided by 3. That means, the positive sequence network, negative sequence network and the zero sequence network, these three networks are connected in series. Why? Because it is clearly said that the sequence currents are equal. So, if you connect them in series, here it is shown series connection. All the three sequence networks connected in series. Therefore, IA1, see here IA1 and this is IA2 and this is IA0. So, IA0 is flowing as IA1, IA1 is flowing as IA2 here. Therefore, all the sequence currents are equal. And then we have to consider the voltage equation. So, in the previous slide it is shown. See here it is shown how to get this matrix equation, and this matrix equation is used for further analysis. Here we come to know from the derivation that the sequence currents are equal and it is equal to the IA0. So, now let us make that IA0 is equal to IA1 is equal to IA2. So, with that you can get the expression for VA0, VA1, VA2, and you please add the three values. So, as you know that VA is nothing but the unbalanced voltage. It can be analyzed according to CL40, the symmetrical component of voltages VA0, VA1, VA2. So, in order to get this VA, we are adding the symmetrical component of voltages. When we add the symmetrical component of voltages, if you add the right hand side parameters together, we will get the IA is equal to EA divided by Z1 plus Z2 plus Z0. And also the equation 4.3 says IA is 3 times of IA1. So, this IA is nothing but fault current. This is 3 times of IA1. Expression is EA divided by Z1 plus Z2 plus Z0. So, this is the fault current expression when single line to ground fault happens at unloaded synchronous generator. The sequence network is like this, sequence network under the fault. Next, we will consider one more derivation, that is single line to ground fault explanation will be used further to analyze the line to line fault on an unloaded synchronous generator. See here we are having lines A, line B and line C, line A, line B, line B and line C shorted. That means line to line fault. If the line to line fault is taken place and it is unloaded, the load is not connected to that, therefore, the current IA value will be 0, no current flows because it is unloaded. Here IB is equal to minus IC, correct. This is the fault current, and here this phase and the B and C phase, they are connected in parallel. See, their end terminals are shorted. Therefore, VB is equal to VC. So, let us use these initial observations for further analysis. See here, we have considered the formula of symmetrical components in terms of tau PS inverse into Vp. This formula from the basics we know. So, Vs is nothing but tau PS inverse is 1/3 of 1 1 1 1 A square 1 A square A, and then these phase voltages VA, VB, VC. Okay. So, now these RHS parameters are here. It is observed here that VA1 is equal to VA2, because see here VA1 is equal to VA2, and since IA is 0 and IB is equal to minus IC from the observations we got, and also the IS is nothing but tau PS inverse into IP. Here the phase currents are this, IA is 0 and IB is minus IC as it is. Then if you simplify this, you will get IA1 is equal to minus IA2 and IA0 is 0. And also we have the voltage equation for the synchronous generator, positive, negative and 0 sequence. Here VA0 is 0, and if you simplify this further, you got VA1 is this and VA2, and VA1 is equal to VA2, it is known. When you equate that, you will get IA1 is equal to this. Since the positive sequence network and negative sequence network, it is noted that VA1 is equal to VA2. That means positive and negative sequence networks are connected in parallel. So it is connected in parallel. It is connected in parallel. So we know that the fault current is IB, and the fault current in terms of symmetrical components you can write IA0 plus A square IA1 plus A times of IA2. And it is proved that IA0 is 0, IA0 is 0 plus A square IA1, and IA2 is minus IA1. So if you simplify this, you will get A square minus A into IA1, that is the fault current. This A square minus J root 3 IA1. IA1 is EA divided by Z1 plus Z2 from the previous derivation. Here IA1 is EA divided by Z1 plus Z2. So you can find the value of fault current, that is IF is equal to 3 times of IF is equal to IF is equal to minus J root 3 EA divided by Z1 plus Z2. So with this formula you can find the fault current. You can find the fault current. Sequence network is very simple. Positive sequence network and negative sequence network, they are connected in parallel. So this is IA1, this is IA2, this is VA1 voltage across the terminals, VA2, and this is Z1, this is Z2, this is EA. How they are connected? They are connected in parallel. See, connected in parallel. This is sequence network, and this is the fault current IF. So easily you can find the fault current and the sequence network from the initial calculations. With this I will be ending this video. In this video we have learned what is unsymmetrical fault analysis, and two types of unsymmetrical faults, line to line fault and line to ground fault, are analyzed in detail. Thank you.